Jai Hind. The topic which we are going to discuss today is operating system services and structure of the subject of operating system. These are the points which we are going to discuss today. System components, operating system services, system calls, programs, structures, virtual machines, design and implementation. Now, when we talk about the common system components, then we are having in OS, since we are aware that OS is acting as a bridge between hardware and software, and it is managing all the resources, as well as it is providing a user interface to the user to operate on the operating system. So on the basis of this, we are having these system components: process management, main memory management, file management, input-output system management, secondary management, networking, protection system, and command interpreter system. We are going to discuss these components one by one. When we say a process management, so first we need to know what is a process. So a process is nothing, it is a program which you write, that is a code which you write, and when you execute it, when you run it, it becomes a process. So a process needs certain resources when you run it. For example, it need CPU time, it need memory, it need files, input-output devices, registers, etc. to accomplish its task. The OS is responsible for the following activities in connection with the process management. And what are these activities? Process creation and deletion, then we are having process suspension and resumption. For instance, some input-output activity comes, then the process need to be suspended, and after some time, when the output activity got completed, it will resume its services. It also provides mechanism for process synchronization and process communication. Since we are aware that the processes within the OS, they need to communicate among themselves when they share some resource. So process management component, it provides support for process communication. When the two processes, they are sharing the same resource, then their action should be synchronized so that the shared data doesn't become inconsistent. And for this, we need synchronization support, which is again provided by the process management module. Another module is the main memory management module. The memory, we are aware, what is a memory? Memory is a large array of words or bytes, each with its own address. It is a repository of quickly accessible data shared by the CPU and input-output devices. Main memory is a volatile storage device. It loses its content in the case of system failure. The OS is responsible for the following activities in connections with memory management. So what are these activities? It keeps track of which parts of memory are currently being used and by whom, decide which process to load when the memory space becomes available, and then allocate and deallocate memory space as required. Another important component is file management. We are aware that file is a soft resource which is provided by the system to us, on which we work upon. So a file is a collection of related info defined by its creator. Commonly, files represent programs, both source and object forms, and data. The OS is responsible for the following activities in connection with file management: file creation and deletion. We are aware when we keep a group of files within a directory, then we need a directory support. Directory creation and deletion is there. Support of primitives for manipulating files and directories. Mapping the files onto secondary storage, that is a hard drive. File backup on a stable, that is non-volatile storage media. Another important component is input-output system management. The input-output system, it consists of a buffer caching system, a general device driver interface, drivers for specific hardware devices, and the OS, it provides support for all these components. Another important module is secondary storage management. Since main memory, that is a primary memory, is volatile and too small to accommodate all data and programs permanently, the computer system must provide secondary storage to back up the main memory. Most modern computer systems use disk as the principal online storage media for both programs and data. And what are the operations responsible in this regard is free space management, storage allocation, and disk scheduling. What is disk scheduling? Basically, when various input-output activities, they are waiting to be performed on the disk, then the OS need to know that which request to be serviced first, so that there is minimum head movement in the drive. So for this, we need certain set of algorithms which make a decision in this regard, and this is nothing, this is your disk scheduling algorithms. Another important component is networking, which is basically required for distributed systems, and we are aware that nowadays all the systems, approximately all the systems, they are working in the distributed environment. A distributed system is a collection of processors that do not share memory or a clock. Each processor has its own local memory, and this thing which we have already seen in the previous lecture. The processors in the system are connected through a communication network, and we need certain set of rules, that is protocols, to communicate, to establish a communication link between two devices. A distributed system, it provides user access to various system resources and access to shared resource. Why we need the access to the shared resource? What are the benefits we are getting? The first benefit is computation speed up. That is, we can parallelly run a program or a process on different systems, and we can have a result in a minimum time. Increased data availability and enhanced reliability. Another important component is a protection system. Now what the protection refers mean? Basically, it means a mechanism for controlling access by programs, processes, or users to both system and user resources. That is, each and every process should perform its operations in a controlled environment. They should access the resource which they are intended to use, that is, which lie in their domain. So the protection mechanism, it must ensure that there is a clear, distinct comparison difference between the authorized and the unauthorized usage. It specifies the controls to be imposed, and it provides a means of enforcement. So these are the various components which we have seen. Now, corresponding to these components, we are having various services which are provided by the OS. The first one is program execution, that is system capability to load a program into memory and to run it. Then we are having another service, input-output service, that is user programs cannot execute input-output operations directly, so the OS must provide some means to perform the input-output activity. Then file system manipulation, program capability to read, write, create and delete the files, communication, exchange of information between processes executing either on the same computer or on different systems tied together by a network. It is implemented via shared memory or message passing. Error detection, it ensures correct computing by detecting errors in the CPU and memory hardware, in input-output devices or in user programs. There are additional OS functions which are provided by the OS. Additional functions exist not for helping the user but rather for ensuring the efficient system operations. And for this, we are having resource allocation, that is allocating the resources to multiple users or multiple jobs running at the same time. Accounting, that is keeping the track of the record, which users use how much and what kind of computer resources for account billing or for accumulating usage statistics. Protection, ensuring that all the access to the system resources should be done in a controlled way. Now, when we talk about the system services, OS services, how you can avail these OS services? You can avail these OS services either with the help of system calls or with the help of system programs. So, what is a system call? It provides the interface between a running program and the OS, and generally they are available as assembly language instructions, and the languages defined to replace the assembly language for systems programming allow the system calls to be made directly. That is, if we are having the system calls written in C, C++, then we can directly call them through our program. Three general methods, basically they are used to pass the parameters between a running program and the OS. The first method is pass the parameter in the registers, that is use the registers to passing these parameters, or store the parameters in a table and pass this table address as a parameter to the register. Or the third mechanism says that store the parameters onto a stack by the program and pop off the stack by operating system. That is, the program will push the parameters, and the OS, it will pop the parameters one by one, that is OS is reading from this stack. So, on the basis of this, since we are having various OS services, so on the basis of the types of OS services, we are having various types of system calls. For program execution, we are having process control system calls. For the file management, we are having separate set of system calls. Then we are having device management system calls, information maintenance, communications, and so on. So, these are the basic different types of system calls which are provided by the OS. Communication models, the communication takes place using either message passing or the shared memory. So, what is happening in the message passing system? In the message passing system, we are having a mailbox in the kernel, and the processes, they are sharing these mailboxes, and they are reading and writing whatever they want in this mailbox, and this mailbox, that is a shared memory, is maintained by the kernel. Whereas in the case of the shared memory, the address or the locations which are being shared between the process A and process B, they lie in the user domain, and this is being shared between the two processes. The kernel do not have any control on the shared memory. Both process A and B, they are having the control on the shared memory. This is how the two processes, they communicate within the system, that is inter-process communication. System programs, they provide a convenient environment for program development and execution. And on the basis, again, these system programs, they are responsible for providing the OS services. So, on the type of the OS services, they are further being classified as file manipulation, status information status, that is the status, it could be your process, it could be your device status, it could be your driver status, anything. File modification, that is file manipulation, directory manipulation system programs. Programming language support, that is your compilers, then the program loading and execution support, communication support, application programs. Most users' view of operating system is defined by system programs, not the actual system calls. These system programs, basically they are using these system calls in their code, and the user is using these programs, working on these programs instead of these native system calls. Now, coming towards the OS structure, the most basic type of system structure is provided by the MS-DOS. And it written to provide the most functionality in the least space, and it is not divided into any module. Although MS-DOS has some structure, its interfaces and levels of functionality, they are not well separated as in other OS. This is the simplest MS-DOS layer architecture structure. Here we are having the ROM BIOS device drivers, we are having MS-DOS device drivers, then resident system program, that is our OS, and above that we are having the application program. This is how the OS is written in the case of MS-DOS layered structure. Another important system structure which is studied widely is Unix. Unix, basically it is limited by hardware functionality. The original Unix OS had limited structure, but now this structure has become very complex. The Unix OS, it consists of two parts, and both these parts, they can be separated. One is the system programs and another one is the kernel. System programs, they are basically being called and executed with the help of shell in the case of Unix. The kernel, it consists of everything below the system call interface and above the physical hardware. It is your kernel. It provides support for the file system manipulation, CPU scheduling, memory management and other OS functions. A large number of functions for one level. This is the Unix system structure. At the lowest level, we are having memory controllers, basically meant for physical memory, device controllers meant for device disk and tapes, terminal controllers for your terminals, that is your display unit, and here we are having the kernel interface to the hardware. And this kernel interface to the hardware, it is provided, we are having signal terminals, terminal handling, character input output system, terminal drivers, file system swapping, block input output system. These are the support which is provided within the kernel to access all these hardware devices. On the top of it, we are having the system call interface to the kernel. And how this system call interface to the kernel being used? It is being used with the shells and commands, compilers are, and interpreter support is there, system libraries are there, which you can use and write the code and make your own system program to avail these services within the kernel. And on the top, we are having the users, that is your application programs. Another important system structure is the layered approach. The OS in this case is divided into a number of layers, and these layers, they are very well defined. Each layer is built on top of the lower layers, and with the help of this, we have achieved the concept of abstraction and encapsulation. The bottom layer, that is layer 0, is the hardware, and the highest layer is always the user interface. With modularity, layers are selected such that each uses functions or operations and services of only the lower level layers. So here we are having layer M-1 and here we are having the layer M. So whatever the operations are written in layer M-1, they are the hidden operations that they are not known to the layer M, and layer M can use the operations of this layer, they can use the services of the layer M-1. OS by two follow this layered structure. Here we are having the hardware, that is your device drivers, various device drivers are there. Here we are having the system kernel, and in the system kernel we are having the support for memory management, task dispatching, device management. Above that we are having various subsystems, and these services can be availed with the help of API, that is application programming interface. On the top of it, the applications are running. A microkernel system structure moves as much from the kernel into user space. This is the aim of the microkernel, that is to make the size of the kernel very compact. Communication takes place between user modules using message passing. And what are the benefits? We can easily extend a microkernel. If we want to make any changes in the microkernel, we can do it easily. Easier to port the OS to new architectures, more reliable because less code is running in the kernel mode, and it is more secure as compared to a kernel approach. Now, the next concept is virtual machines. So, basically what is a virtual machine? Virtual machine basically takes a layered approach to its logical conclusion. It treats hardware and OS kernel as though they were all hardware. That is, we are having a system. Here we are having OS, above it we are having applications running on OS, and here we could have the VM support. And on top of this VM support, we could have various virtual machines. That is, each virtual machine is giving an illusion that this is the OS which is running on the actual hardware. Here we are having the hardware, whereas they are running on the top of another OS, which is your host OS. A virtual machine, it provides an interface which is very much identical to the underlying bare hardware. The OS creates an illusion of multiple processes, each executing on its own processor with its own memory, and this memory is a virtual memory. The resources of the physical computer are shared to create the virtual machines. CPU scheduling can create the appearance that users have their own processor. Spooling and a file system can provide virtual card readers and virtual line printers. A normal user time sharing terminal serves as the virtual machine operator's console. So here we are having, if you look at the non-virtual machine, then we are having the processes, they are running on a kernel, and this kernel is directly interacting with the hardware. Whereas in the case of the virtual machine, we are having hardware, we are having virtual machine implementation, many other implementations, they support that there may be a OS or kernel, which is your host. Above this virtual machine implementation, we are having various virtual machines. Here we are having kernels. These kernels, they can be identical or different. For example, here we can have Windows OS, here we could have Unix, here we could have a Mac, for example, and so on. So we could have same or various flavors of the operating system each running in different virtual machine. And all these virtual machines, they are having their own sets of process. So it is giving the illusion to the user that all these processes, they are directly operating on the hardware. Whereas if we look at the broader aspect, then all these processes, they are sharing the space, that is, they are sharing the hardware with other virtual machines. And this hardware has been virtualized with the help of virtual machine implementation. It is a special software, for example, VMware and so on. What are the advantages or disadvantages of virtual machine? The virtual machine concept, it provides complete protection of system resources, since each virtual machine is isolated from all other virtual machines, and this isolation permits no direct sharing of the resources. If any damage happens in virtual machine 1, then it will not put an impact on other virtual machine, for example, VM2. A virtual machine system is a perfect vehicle for OS research and development. System development is done on virtual machine instead on top of a physical machine. So the physical machine does not get corrupt. The physical machine, they can continue with their normal operation. The virtual machine concept is difficult to implement due to effort required to provide an exact duplicate to the underlying machine. So they are putting some kind of complexity over the system. Now, when we design an operating system, then what are the system design goals? Since we are aware that the OS, it is providing an interface between the hardware and the user. So, from these viewpoints, we are having two basic goals, one corresponding to user goals and other corresponding to the system goals. Now, what the user goal says? It says that the OS, it should be convenient to use. It is easy to learn. That is, if it is a CLI based OS, then in that case, the commands, they should be easy to learn, reliable, safe and fast. When we are looking from the system perspective, then what are the requirements, what are the goals required by a computer system? Since the resources, they are residing on the computer system, so it demand OS should be easy to design, implement and maintain, as well as it should be flexible, reliable, error-free and efficient, and it should manage the resources efficiently. This is all about the OS services, components. We also see a brief introduction of system programs, system calls, and what is a virtual machine. This is all for today. Thank you and Jai Hind.